today we are having, most of the things we'll be learning from the videos, right? That is animated videos. Because in the last class, we have seen this processes, purification of organic compound. That is what? Filtration. Vishnupriya was there. So filtration we have seen, recrystallization we have seen, sublimation we have seen, distillation we have seen, fractional distillation we have seen or not? Vishnupriya? These I remember that we don't have seen these things. That is steam distillation, differential extraction, chromatography, these we haven't seen. Distillation under the reduced pressure, that's also we haven't seen. And fractional distillation, have we seen or not? Please tell me that. Vishnupriya, what do you say? From 6. Okay. So 6, 7, 8, 9 we will be seeing from here. And these things we will be seeing from the animated videos, guys. Right? Because it will take more time to draw the each and every diagram and all. So it will be better to see from the animated videos that I am going to show you from here. And after that, we will be looking ahead.
Sir, I think we need to see the fractional distillation also, sir.
We haven't seen fractional distillation.
Yes, sir. I have no course only till distillation.
Okay, we will be learning from the fractional distillation only. Okay. One more video I'm going to show you guys. Just give me a moment. So guys, if I will be going to ask you one question from this video, question is what? A long carbon chain, this one, or this one, which will be having more boiling point? One or two? Which will be having more boiling point? Who will be telling me, guys? Please tell me what will be the right answer for this question. One will be having more boiling point, or second will be having the more boiling point. Vishnu Priya, what do you say? One. Kaniska? One will be having more boiling point, or two will be having more boiling point? What do you think? Everyone is saying one. Okay. So guys, you have seen the videos very carefully, it means, right? So long carbon chain will be having the more boiling point. Small carbon chain will be having the lower boiling point, right? Is it okay? So now we are going to see about what? Distillation under reduced pressure, right? We are going to say this now. No, actually, I haven't given the video. Just a minute. So we have seen, guys, about what? So we have seen distillation under reduced pressure, right? Now we are going to see about what? Steam distillation.
Steam distillation. The process of steam distillation can be applied for the separation of a mixture of O-nitrophenol and P-nitrophenol. In this process, water vapors carry along with them vapors of O-nitrophenol, which is more volatile, and then get condensed in the receiver. P-nitrophenol, with higher boiling point, remains in the distillation flask. Steam distillation. The process of steam distillation can be applied for the separation of a mixture of O-nitrophenol and P-nitrophenol. In this process, water vapors carry along with them vapors of O-nitrophenol, which is more volatile, and then get condensed in the receiver. P-nitrophenol, with higher boiling point, remains in the distillation flask.
Is it okay, everyone? So we have seen about distillation, steam distillation, distillation under reduced pressure. Now we are going to see about differential extraction, right? Differential extraction.
The technique of liquid-liquid extraction is a form of solvent extraction which is often referred to simply as a separation, and we do this using a separating funnel as shown on the screen. The technique can be used in a range of contexts, and it's important that you understand why you're carrying out a separation in the experiment that you're doing. In this demonstration, we have a solution of a product of a reaction in an organic solvent, which in this case is diethyl ether. We are going to wash the solution with water to remove impurities which are water soluble. The first step is to remove the magnetic stirring flea from the reaction flask, and we need to wash this with ether to ensure that we don't lose any of our product. We now need to pour the solution of our product into the separating funnel, taking care to avoid any spillages, so it's wise to use a small glass funnel as we pour. Then we can rinse our reaction flask with more ether to ensure that no product is lost. Now we add the water which we're using to wash our reaction mixture with. It's important that you pay attention to your script, which may specify a different solvent and a particular volume that you need to work with. Next, you need to place a stopper in the neck of the separating funnel, and you must ensure that you don't allow this to fall out at any point while you're handling the apparatus. Secure the stopper with one hand and carefully invert the separating funnel. Now you can gently shake the funnel while periodically opening the tap to release pressure. Normally you carry out these steps several times to ensure thorough mixing of the two layers. And then with the tap closed, you can carefully replace the funnel in the ring on the clamp stand. Here you can clearly see the two separate layers in the funnel. In this case, the denser aqueous layer is at the bottom and the ether layer is on top. However, you should never make assumptions about which layer is which, and you may be given instructions that tell you how to test which layer is organic and which is aqueous. Before running any solvent out of the funnel, you must first remove the stopper. Not doing so is a common error which will prevent the solvent from running freely. Now you should place an appropriately sized conical flask under the separating funnel before carefully opening the tap to allow the lower layer to run out. You should watch patiently as the interface between the two layers moves towards the tap so you are able to stop the flow once all of the lower layer has been removed. Remember that in this case, the lower layer was the aqueous layer. Now you can remove this flask and place a second clean conical flask under the separating funnel to collect the upper layer. As always, you should check your script to see what you've got to do next. You may be expected to return one of the layers to the separating funnel to carry out further extraction steps. In this case, however, we are simply going to dry the organic layer using magnesium sulfate. Other drying agents that may be used could include calcium chloride and sodium sulfate, so make sure you read the script before proceeding. If the drying agent forms clumps as shown here, that's a sign that the solution is still wet and that more drying agent is required. When you can see a snowstorm effect like this, you know that the solution is dry and that no more drying agent is needed. You can now remove the drying agent by gravity filtration before consulting the script once again to identify your next step.
So one more that we are going to see about what? Chromatography, right?
Thin layer chromatography (TLC) is a chromatography technique used to separate non-volatile mixtures. As well as other forms of chromatography, in TLC there is a mobile phase, which may consist of a solvent or solvent mixture. And there is a stationary phase, which is a plate that coated with a thin layer of adsorbent material, usually silica gel, aluminium oxide, or cellulose. To run a thin layer chromatography plate, a pencil line is drawn, about 1.5 centimeters from the bottom edge. Also, the plate can be labeled using a pencil to show the original position of the drop. Thin layer chromatography can be used to identify compounds present in a given sample mixture. A small drop of the mixture is placed on the baseline of the thin layer plate. And similar small spots of known compounds are placed alongside it. When the spots are dry, the TLC plate is then placed in the chamber so that the spots do not touch the surface of the eluent in the chamber. And the lid is closed. The solvent moves up the plate by capillary action, meets the sample mixture and carries it up the plate. The separation is based on differential partitioning of the sample components between the mobile phase and the stationary phase. The component which has less affinity to the stationary phase, consequently, less interaction, travels further up the TLC plate. And the component which has more affinity to the stationary phase, consequently, more interaction, travels slower on the plate. This separation can be carried out according to the nature of the mobile phase, which is non-polar, and to the TLC plate type, which is generally a polar stationary phase. In this case, this method separates analytes based on their affinity for a polar stationary surface, such as silica gel. The more polar the analytes are, the more retained they will be on the stationary phase. The more hydrophobic they are, the more they will prefer the mobile phase, and as a consequence, they will move higher up the plate. The solvent is allowed to rise until it almost reaches the top of the plate. That will give the maximum separation of the components. The plate should be removed from the chamber before the solvent front reaches the top of the stationary phase. Then this front is marked. The plate can be dried in ambient air or under the warm air of a dryer. The plate is visualized under the UV lamp or by using certain chemical reagents if the substances of interest are colorless. Some plates are pre-coated with a phosphor, allowing many compounds to be visualized by using ultraviolet light. Or a derivatization of the sample with fluorescent reagent can be carried out before running the TLC plate. As soon as the UV source is switched off, the spots will disappear again. Therefore, the positions of the spots should be marked by drawing a pencil circle around them. And the retention factor of each component is determined. For chemical visualization of stains, various visualizing agents react with the spots to produce visible results, such as iodine, ninhydrin, potassium permanganate, and vanillin. The plate can be immersed in these chemicals or sprayed. Once visible, the RF value or retention factor of each spot can be determined by dividing the distance the compound traveled by the distance the solvent front traveled, using the initial spotting site as reference. A compound with a lower RF tends to have more polar functional groups than a compound with a higher RF. Based on the RF values, compound A is the most polar and compound C is the least polar. The retention factor of the spots in the mixture is determined and compared with those of the known compounds. In this sample, we found the presence of the compound A and the compound C.
So guys, we have seen what? So we have seen almost all the purification methods here, right? So filtration, recrystallization, right? Then we have seen what? Separation of crystal, drying crystal, removal of color, sublimation. Sublimation you can do at your home as well, right? You have to do what for that? Just you have to burn what? Camphor at your home. And after that, fractional distillation, right? Distillation under reduced pressure, steam distillation, and differential extraction with separating funnel. So column chromatography is still left, and paper chromatography we have done. So one is what? Column chromatography, that we have to see. Just give me a moment.
This video outlines the method for carrying out column chromatography. You may be given slightly different instructions when you do this in the lab, but the principles will be the same. First of all, a small piece of cotton wool is placed in the bottom of the column to prevent solid material from going into the tap. Different columns may have different types of tap, but obviously the idea will be the same. Next, a small amount of sand is poured in to a depth of about 1 centimetre. Here you can see the sand forming a level surface on top of the cotton wool. We then take the appropriate amount of silica in a beaker, and this is then made into a slurry using the solvent we're going to run the column with. This solvent is known as the eluent. Here you can see us swirling the silica with the solvent before pouring it into the column very carefully. Again, a funnel should be placed in the neck of the column to assist with pouring. And you will need to occasionally swirl the beaker to ensure that the silica doesn't settle out in the bottom of the beaker. Where appropriate, more eluent should be added to reform the slurry to assist with pouring. You may need to do this several times. Should the level of the eluent get close to the top of the column, then some of it should be removed by opening the tap. We can run this into the beaker, which will then assist us in making a slurry with the remaining silica. And finally, we've transferred all of our silica into the column. Now we need to run some of the eluent out of the column so that it comes down to the level of the silica. It's crucial that you don't allow the silica to run dry, so you need to keep a close eye on the level of the eluent and close the tap at the appropriate moment. Here you can see we've run the eluent down to the correct level so that the top of the silica has not dried out. The next stage is to load our crude compound onto the column. First of all, we need to dissolve it in a small amount of the eluent. It's important to ensure that all of the crude compound has been dissolved. And then the resulting solution can be added to the column using a glass pipette. Here you can see the solution is being added evenly around the sides of the column. Now we add some sand to a depth of about 1 centimetre on the top of the column. This will protect the silica as we add eluent. And here you can see us topping up the column with eluent. And we're now ready to run our column. So we open the tap at the bottom of the column, and this allows us to collect our first fraction. In this case, we're collecting the fractions in test tubes, but depending on the size of your column, you may use sample vials or even conical flasks. Once collection is complete, we can close the tap momentarily to move on to collect fraction number 2. And this process can be repeated any number of times to collect as many fractions as are required. Because our compound is coloured in this case, we can actually see it moving down the silica. This will give us a good indication as to when it's actually eluting from the column. In cases where you can't see the compound because of any colour, you can use TLC to analyse the fractions to identify the presence of different compounds. And as the level of the eluent approaches the sand, it's important to make sure that you top it up. We can then continue to collect fractions, and in this case you can see that the yellow band in the silica is approaching the bottom of the column. If we look closely at this particular fraction, we can see that the solvent has a yellow colour, telling us that our compound is eluting. Of course, in other cases, as mentioned previously, you'd have to use TLC to identify the presence of a compound. And here we have a full set of fractions. We can now collect any compounds that are present by removing solvent, and this would most commonly be done.
So guys, one by one we have completed all the experiments that you can say here, sublimation, decrystallization, everything we have done here. So hope you have understood all these things. So we will be going ahead with the next topic, right? Now we are going to see about what? See guys, today we are going to see so many, experiments, right? That the presence of the elements like hydrogen, halogen, sulfur, oxygen, so are they present in the reaction or not? We are going to see that. That the test of the, how we can test, that we are going to see here today. Is it okay, everyone? Any doubt? So what we will be going to see today? So test of different elements, that whether they are present in the reaction or not. So for that we are having different types of experiments we are having, right? So first of all, you can see here hydrogen gas is there. Now these days hydrogen, our government or even every institution is working about the hydrogen as a fuel, right? Earlier we were having a limited resources like kerosene, petrol, diesel, that, but now these days you might be seeing that electric cars are also running in the streets, right? So but not up to the electric cars. We will be going ahead from the electric cars also, that the new generation, the new fuel will be the hydrogen fuel, right? And that will be cost effective as well, and that are easily available also. So our government and the research institutes are working on this to bring a car model. Even this hydrogen model car has been launched also, right? Launched meaning that the process has been done for this as well, right? So you will be seeing in coming years that you will be seeing that your car is running on hydrogen, right? And that will be cost effective as well, because right these days we are having 110 rupees per liter petrol, right? And almost 100 rupees of diesel. So they are very expensive for us, right? So government is planning, even institutions are planning to reduce this, to cut this, overhead charges, and to come into a new set of fuels, or you can say that type of vehicle where these can be used. Like not only the hydrogen, we are working on the ethanol as well, right? Ethanol will be our fuel for our cars, for our scooty, for our vehicles. We will be using ethanol for our biofuel. That is known as what? Biofuel, that we will be using, because ethanol is very easily available, because we are getting, India is a country of what? Agricultural country, right? So we can get ethanol from so many ways, from the agricultural products, right? So that will be more easier for us, and that the cost will be around 30 to 40 rupees per liter. Getting my point? Now this day we are having a petrol of 110 rupees per liter, but the cost of ethanol will be somewhere around 40 rupees per liter, right? So many fuels are, government is planning to bring so many kinds of fuel. Not only we have to depend on the petrol and diesel, as we have done from the last so many years, you can say in hundreds of years, but the changes are being done, right? You might have seen the electric cars are very easily available on roads, right? EV cars, even the EV rickshaws are also available these days. So we are going to work on this. chromatography that we have seen, right? So that you can see the real life example that we can see that the hydrogen is a new fuel for the India, not only the India, for other countries as well. Is it okay, everyone? Any doubt to anyone, then please tell me. No. See here, detection of carbon and hydrogen. How we can find that carbon and hydrogen, right? There is a, how we can find the carbon or hydrogen in any reaction. See here, detection of carbon and hydrogen are detected by heating the compound with copper 2 oxide. Carbon present in the compound is oxidized to carbon dioxide, tested with lime water, which develops turbidity, and hydrogen 2 water tested with anhydrous copper sulfate, which turns blue, right? So what is the reaction for this? We have to see the reaction, right? Let's suppose carbon and hydrogen are there, right? Carbon and hydrogen. Is it okay? When you will be heating, what you will be going to do? When you will be heating with, heat with what? CuO. Okay, CuO. So what you will be going to get here? Two things. One is what? That is carbon, and hydrogen, right? And carbon will be forming what? CO2. CO2, here it will be what? H2O. Is it okay? So this H2O, what will happen? See, it will turn CuSO4 to which color? That blue. And here what will be happening? Turbidity, right? CO2, you can see here CO2, that will be in next step, it will be what? CaOH2. CaOH2, right? And turbidity. So these are the reactions that you can see by which you can find what? The presence of carbon and hydrogen, right? Now see here, what will be there? There is a small, see, this is very important. There is very important reagent is there. That is what? Lasing's test. This is very important, and these are coming in examination as well. LASSAI GENS, Lasing's test, right? This will give you idea that how this can be formed, right? So now we have found carbon, we have found hydrogen, right? So Na plus C plus N, it will give what? NaCN. It will be giving what? NaCN. Now 2Na plus what? S. It will be giving what? It will be giving Na2S. And NaX, Na plus X will be giving what? That will be NaX. So from organic compound you can see here what? From organic compound we have got what? This change in ionic. Is it okay? So these are the tests that you have to write, guys. Please have a note of these things. This will help you to understand the presence of what? The carbon and hydrogen. So if you are done with this, then have a break of 5 to 10 minutes, then we will be back. Everyone is here? Yes, guys. Okay, so we are seeing about what? Lessing's test, right? Now we are going to see about what? See, we are going to see about what? That is test of nitrogen. Test of nitrogen is what? What is this test of nitrogen? How will you test nitrogen? Can anyone tell me? How we can test nitrogen? Who will tell me? Anyone? See, guys. See, we will be testing by sodium fusion extracted, right? We will be testing sodium, nitrogen, sulfur, everything by sodium fusion extract. That is from fused by massing of boiling it with distilled water, right? That we have got. If you will be in the last reaction that I have found, if you will boil it by distilled water, you will be getting what? Sodium fusion extracted, right? This is known as sodium fusion extract. So if sodium fusion extract is treated with what? In the presence of nitrogen, see here, what it will be giving? Boiled with FeSO4. So what will be happening there? Then boiled, and then what will be happening? Oxides, right? Oxides Fe2 plus will be, you will, is it okay? And if H2SO4 is added, H2SO4 is added, then what will be happening there? It will give the color, and that color is known as what? Persian blue. Which color? Persian blue color. Is it okay, everyone? Persian blue color. Now, what will be happening after this? If, see here, 6Cn minus and Fe plus 2 that we have seen there, Fe plus 2 will give what? That is Fe CN6, that you will be learning. This is a coordination compound that you will be learning in class 12, right? 4 minus and Fe plus 3 XH2O, right? It will give what? Fe4, right? CN6, Fe4, and after that, what is giving here? Fe CN6, right? Dot XS2, right? This is known as what? Ferricyanide. This is known as what? Ferricyanide. Is it okay, everyone? Or you can say what? Iron 3, because the oxidation state of this iron is what? 3 here. That's why we will be writing here iron 3. Hexa, see here, CN6 is there, so hexa, and CN is what? That is cyano. So hexacyano, cyanido, right? Hexacyano tetraacetate. That is what? Tetraacetate. Cyanotetraate and 2. Is it okay? Ferrocyanide, ferricyanide, that you can write about what? Iron 3, hexacyanide, cyanide tetrate 2. Is it okay? Now, how you will be testing the sulfur? If you have to find that sulfur, whether it is there in the reaction or not. So how you will be finding the sulfur? See here. Again, you will be taking what? Sodium fusion extract. Sodium fusion extract that we have done in the very first reaction. Sodium fusion extract. Yes. And see here. See what we will be going to do here. With acetic acid. If you will be treating it with what? Acetic acid. You will be getting plus acetic acid plus lead acetate. Lead acetate. You will get what? That is what? You will get black PPT. What? Black PPT, right? Black PPT. And the reaction that we are knowing, that is what? S2 minus plus PB 2 gives what? PBS. Is it okay, everyone? So this black color will say what? There is a presence of sulfur, right? Now, next one is what? B. Is it okay, everyone? Have you written this reaction? Yes or no? Please tell me. See. Now, next reaction is what? That is sodium nitro oxide. It will give what? Violet color. Violet color. Here the reaction will be what? S2 minus plus Fe CN6, right? Not CN6, CN5 and NO2 minus. So it will give what? FeCN6, FeCN5 plus NOS4 minus. So we can see here what? Nitrogen plus sulfur. Nitrogen plus sulfur. See here. Will give what? Na plus S plus C plus N. And this is what? NaSCN. NaSCN. And in the presence of what? Fe plus 3. Fe plus 3. It will give what? What it will be giving? See guys, you have to note first this reaction. See. Test of sulfur we have seen. Test of nitrogen we have seen. Fe 4 FeCN6S2.S2 that will be giving there, right? We have to see test of halogen then. The basic funda is what? Ledging test is used for what? For the nitrogen, sulfur and halogen present in any organic compounds are detected by Ledging's test. Done, everyone? So we have seen this. Now test for halogen. If we have to see for test for halogens. So how we will be going to see? See here. This we have seen. This also we have seen, right? Phosphorus. We have to see for first halogen, then phosphorus will be going to see, right? So write about the test of halogens. How we can test halogens? Can anyone tell me? See, when there will be a reaction between AgNO3 plus NaX, AgNO3 plus NaX, right? So what it will be giving here? In this case, what it will be giving here? AgX plus NaNO3. AgX plus NaNO3. Is it okay? Any doubt to anyone? So there will be a test of what? There will be a test of halogen. If it is what? See, what happens here? The extracted is acidified HNO3, then treated with what? AgNO3. That the extracted that we have seen earlier, if it is acidified with HNO3, then treated with AgNO3, then what we will be going to get? That is white precipitate soluble in NH4OH, indicates the presence of chlorine. And it is what, a yellow precipitate will be formed here. That is strongly soluble in NH4OH. See here, yellow precipitate will form. Yellow precipitate will form. That will be strongly soluble. Is it okay? Any doubt to anyone? Now, one more thing is there. See, presence of Br, when test of halogens will be there, presence of Br in the solution will give what? That a yellow precipitate insoluble NH4OH indicate the presence of I. So these are the tests of what? Halogen that we have seen. We have to test for the hydrogen also, carbon also in today's class. So rest of the things we'll be seeing in the next class. 1, 2, 3 tests are there that we'll be seeing in the next class, oxygen test. But from here you have to do what? The class assessment. Just give me a moment. If after class assessment, if I will be getting time, then we will be doing some more part of this class. Check guys whether you are able to see the class assessment or not. Class assessment is not visible to you guys. Is it visible now? Okay. So now start doing that. sorry for the interruption, guys. I would like to tell you one thing. There is a method, Khajal-Dahal's method, right? Although we'll discuss tomorrow, but I'm going to write the formula for finding the, if there is finding of the percentage of nitrogen there, right? So how you can find that? There is a formula that will be used there. That is what? 1.4, right? V into what? N, right? The percentage that has been, the amount of nitrogen that has been given there, and upon what? See here. N is what? V is what? W is what? That I am going to say. 1.4 into V into N. V is what? Volume, right? V is what? Volume, right? No. And what is, that will be in ml, right? N is what? That is normality. And normality is what? That you might have learned in the very first chapter. If you haven't learned, then I will tell you what. And W is what? That is weight. That is what? Weight of the sample. Weight of the sample in gram, right? And this will be in what? ml. Is it okay? Now, if you will be going to ask me what is this normality? Normality, formality, you might have learned in your earlier classes in the first chapter, right? What is this normality, right? Normality, formality, molality, you might have learned these things in your first chapter. So normality is what? That is number of gram equivalent of solute upon volume. Number of gram equivalent of solute upon volume. Is it okay? What is this normality? Gram equivalent upon volume. Normality is what? Gram equivalent upon what? Guys, upon volume. So you have to apply this. If any question is coming on this formula, so you have to apply this and then you have to proceed with the question. Is it okay? One more method is there to find the percentage of nitrogen. That is what Damas method, right? So I'm going to give you the formula for that, right? How to find the percentage of nitrogen by Damas method, right? So if you want to write, then please have a note of this. First of all, volume of nitrogen at STP. Guys, please have a note of this. This will help you to solve your question by Damas method, right? So first write the formula. Volume of nitrogen at STP is what? P1 V1 into 273 upon 760 into T1. Write the formula P1 V1 V1 into what? P1 V1, what will be there? Into 273 upon 760 into 273 upon 760 into what? What will be there? Guys, what do you think? What is the formula that we are having? 760 into what? P1 V1 into 273. Temperature will be what? 273. And rest will be what? What do you think? By the mass method, we have to find what? P1 V1 into 273 upon 760 into T1. T1 is what? Temperature, right? So you have to apply what? T1. So this is one step, right? And you have to find what? You have to find what? The percentage of nitrogen. So for percentage of nitrogen, you have to apply what? 28 into V. 28 into V into 100 upon 224 upon 28 into V. What is the formula for that? 28 into V, that is volume, into 100, right? 28 into V into 100 upon 22400. 22400 into small m. I will tell you that is what is this small m. Please have a note of this first. 28 into V into 100. 28 into V into 100. Write this first. 28 into V into 100 upon what? 2240, right? You have to write what? 2240, right, guys? Into small m. You have to write what? 2240 into small m. So 22400 into small m. Small m is what? Molality. Use this formula to find the percentage of nitrogen by Damas method.